the next section, let's repeat this design process for a real case. The input information in here is written here. So the angular speed of the Pelton turbine is 400 RPM. The head of the turbine is 1320 foot. It's not a small value at all, about 450 meter head. Okay, the other one is the diameter of the jet, which is 6 inch or half a foot, about 15 centimeters. This is the diameter of the jet, and we have used just one nozzle. And the overall efficiency is about 85%. As I told you in the previous section, the efficiency of the Pelton turbine is smaller than the efficiency of Francis and Kaplan, and the maximum efficiency is about 88%. Okay, let's start the procedure of design. At the first step, you have the head. Head is given here, so you can simply compute the required jet velocity. CV is a constant, 98.98, and the process is straightforward. So the jet velocity which leaves the nozzle is about 286 foot per second. And at the next step, you can easily compute the flow rate, which is the product of the area of the jet and the velocity of the jet. The velocity of the jet is computed here, and the area of the jet is given based on the diameter of the jet. So this is which is a circle. So this is the area, and this one is the velocity. So the capacity or the flow rate of the nozzle is about 56 cubic foot per second. And also we have just one nozzle, so Q is equal to Q. The third step is to compute the braking horsepower, P horsepower, or the braking horsepower, based on step 1. So you can start this procedure from any item based on your given information. For example, you can start from this relation and compute P based on Q, or you can start from this relation based on the given information. This loop could be started from anywhere. Okay, the step 3 is the braking horsepower, which is equal to the product of the overall efficiency, gamma H and Q. But because I have written the braking horsepower, so their unit is horsepower, I need a unit conversion factor here at the denominator. So overall efficiency is given, and gamma is the working fluid is water. So this is the gamma of water at standard temperature. The capacity or the flow rate is computed in item 2. Head again is given, and this is the conversion factor. So the braking horsepower of this turbine is 7130 horsepower. The fourth step is to compute the specific speed of this turbine. It should be computed. It should be considered that if at the first step you have to compute the specific speed. If the specific speed of the turbine is greater than a threshold, or a limiting case, or is a large value, so you have to change the Pelton turbine to Francis turbine or Kaplan turbine. But in this case, as you see the result, the specific speed is a small value, so the choice of the an impulse turbine or the Pelton turbine is a good choice for this case. So the NS is the product of N and the braking horsepower, the square root, and head at the denominator, So this is for 400 RPM, and the specific speed is 4.25, which is small. So the Pelton turbine is a good choice for this case. Step 5 is step 5 here is the speed ratio, which is the ratio of U and V sub J. Here I have, which equals 0.45, And in this case, I've computed the velocity of the jet here, the velocity of the jet. So the circumferential velocity is known, and also the circumferential velocity is related to the RPM of the turbine and the diameter of the runner or the pitch diameter. So in this relation, the only unknown is D. This is the runner diameter is approximately 6.26 foot. And at the last step, I want to compute the number of buckets or the number of cups using this relation, 15 plus half of the jet ratio. D or the runner diameter is computed here, and the jet diameter is given. So the approximate value of the number of, which should be an integer, the number of cups is 21, and at the last step you can compute the cup size. I ignored this step here. You can yourself compute the size of cups based on the computed value for the diameter of the, or the given value of the diameter of the jet. The last item, or the last step of this design, is to compute the power based on our calculations in the previous section of these videos. I mean the part about the control volume analysis of the Pelton turbine. In that part I wrote the conservation of momentum, and I computed the best and the optimum speed ratio. In that video I obtained this relation that the power, or the braking horsepower, is equal to the is equals twice the product of the density, the capacity, the circumferential velocity, and the jet velocity minus the circumferential velocity. You can substitute the information of this problem in this relation, and also convert the units from standard units in English engineering to the horsepower. And also don't forget the efficiency here. So we have the efficiency, so you have to multiply efficiency to this relation, and the final brake horsepower will be 6800. And compare the result of our calculations here with the result of item 3. So you can see we have approximately the same result from the calculation of this problem, and also the calculations I presented in the previous section based on the control volume analysis.